Take a photo of the people you love. Now toss it into a fire. The paper curls, turns black, and floats away as smoke. Gone forever, right? Wrong. Physics says every tiny detail of those faces is still there, hidden in the smoke, the heat, and the ash. With a good enough computer, you could rewind all of it and build the photo back perfectly. This is the strictest rule in the whole universe. Information can never be destroyed. The cosmos never forgets anything. Ever. If it did, the past would vanish and tomorrow would be impossible to predict. But there is one place in space where this rule seems to snap clean in half. Drop that same photo into a black hole and it crosses a line called the event horizon. Past that line, the math that holds reality together just stops. The photo isn't hidden. It's deleted, wiped off the universe's hard drive. And that is supposed to be impossible. Funny how the cosmos keeps its scariest glitch locked behind a wall of gravity, in the one spot we can never go and check. What if the accident has something to hide? To see why this keeps physicists awake at night, look at what a black hole really is. Picture a trampoline. Put a bowling ball in the middle and the surface sags into a dip. That dip is gravity. Roll a marble past it, and the marble curves inward instead of going straight. That's the exact same reason the moon circles the Earth. Now make the ball heavier. Then heavier again. So heavy that the trampoline stops sagging and folds into a bottomless drain. Anything that rolls in never rolls back out. Squeeze a giant star down small enough, and that is exactly what happens to space itself. The rim of that drain is the event horizon, the point of no return. Even light, the fastest thing that exists, isn't quick enough to climb back out. The monster black hole at the center of our own galaxy weighs about 4 million times more than the Sun, all folded into a ball smaller than our solar system. For a long time, we thought black holes were just the universe's trash cans. Stuff falls in, stays forever, case closed. Then in 1974, a physicist named Stephen Hawking spotted something that broke the whole idea. Black holes are not perfectly black. They leak. Incredibly slowly, a black hole gives off a faint mist of particles and shrinks, like a giant ice cube melting in an empty room until there's nothing left but a puddle. Hawking argued about what this meant for the rest of his life, and even flipped his own answer more than once. When the man who mapped black holes can't make up his own mind, you should probably sit up straight. Because here's the trap it sets. If the black hole melts away completely, where did our photo go? Hawking's math said the mist leaking out is pure random static, blank. Imagine feeding a whole encyclopedia into a shredder and getting back a pile of empty confetti, not scrambled, erased. And if information can truly be erased, then cause and effect stop working, and reality itself becomes a story that doesn't add up. For 40 years, the smartest people alive went to war over this one problem. One rulebook, Einstein's gravity, said the information is destroyed. The other rulebook, quantum physics, said destroying it is flat out impossible. Both had passed every test we ever threw at them, but only one could be right, and whichever one lost would drag a huge chunk of what we know down with it. Then came an answer so strange it sounds like a movie script that got rejected for being too silly. A physicist named Leonard Susskind realized the photo never reaches the bottom at all. The instant it touches the event horizon, the flat pattern of information that makes it a photo gets smeared across the black hole's surface, like the shiny sticker on a credit card. That sticker is completely flat, just 2 dimensions, yet tilted in the light, and a full 3-dimensional picture jumps out. The event horizon does the same trick. It's the ultimate hard drive. Everything that falls in leaves a perfect, flattened imprint on the outside surface. And as the black hole slowly leaks its mist, that mist brushes past the surface, picks up the stored data, and carries it back out into space. Nothing is ever lost. It's just copied from 3D into 2D and quietly whispered back to the universe, one particle at a time. In 1993, another physicist, Don Page, found a way to check this. He showed that if the information really is coming back, the mist can't stay blank forever. About halfway through the black hole's life, that random static has to start turning back into a signal. Now here's the part that should make your hair stand up. The surface is split into pixels, and each pixel is smaller than anything you can picture. If a single atom were blown up to the size of the entire visible universe, one of these pixels would be about the size of a tree. Each of those unthinkably tiny pixels holds exactly one piece of data. And if the amount of information didn't match the surface area perfectly, off by even 1/1000th of a percent, the whole thing would break the laws of heat, go unstable, and detonate, taking a piece of the galaxy with it. But it never does. It balances. Every single time. It's a safe with 1,000 spinning dials, and the universe lands all of them on the exact right numbers on the first try, in the dark, without looking. For a blind, random puff of cooling gas, the cosmos sure knows a suspicious amount about flawless data storage. So what if we could actually build this? A hard drive that works like the edge of a black hole? The world would be unrecognizable. And believe it or not, we are already trying. In 2014, scientists at Fermilab near Chicago built a machine called the holometer. For years it fired lasers back and forth, hunting for the faint pixel jitter that would prove our own reality is secretly a hologram. After all that money and effort, it came back nearly empty-handed. The universe simply refused to show its pixels at any scale the machine could reach. In 2019, a small army of scientists linked telescopes across the entire planet, all to capture a single blurry photo of one black hole's shadow. One fuzzy orange ring, and it was hailed as one of the greatest achievements of the decade. We needed a camera the size of the Earth just to take that one picture. Meanwhile at CERN, we built a 27-kilometer ring, spent billions of dollars, and smashed particles together at almost the speed of light, and it still can't get anywhere near the physics a black hole handles for free, in total silence, all day long. A spinning black hole even keeps usable energy locked in its spin. In theory, you could pull raw power straight out of it, something no engine we've ever sketched on a whiteboard can do. Think about what mastering this would mean. You could store the entire internet, every video, every book, every photo ever taken, on a single grain of sand using zero electricity. Today, we build supercomputers the size of football fields that need their own power plants, just to copy a sliver of what the empty dark does for nothing, without ever crashing, without ever losing a single byte. Random forces, apparently, run a 5-star data center and never once pay the electric bill. So step back and really look at what we're staring at. A black hole grabs the two rulebooks of physics that can't stand each other. The one swearing nothing can ever be lost, and the one swearing everything that falls in disappears, and somehow makes both of them true at the exact same time. It catches the precise instant reality should shatter, and instead folds it into a flat, flawless hologram, so that not one single memory is ever erased. A self-correcting machine, balancing on the edge of a razor, humming quietly in the dark where nobody is watching. We like to tell ourselves it's all just an accident. Random rocks, random gas, a lucky mess that happened to cool down at exactly the right speed. It's a comforting story. It helps us sleep at night. But look one more time at the math holding that machine together, perfect down to the last decimal, spinning every dial to the right number on the very first try. Who calibrated this, if no one calibrated it?